So, welcome everybody. My name is Doelf Broekaart. I'm the director within the Simulation Center of Excellence. My background is in mechanical engineering. So I have a bachelor degree in mechanical engineering and a bachelor degree in plastic science. I've been in the software and engineering industry for quite some years. I also manage quite some specialized people, the really technical specialists who actually do the work. I have done the work myself as well, so I know quite well how to do those very difficult simulations myself. But managing those FEA specialists is a different kind of challenge. I won't get into that today. So the agenda. At first I will give a short introduction on Simulion and the TECHNIA Simulation Center of Excellence. Further down I will talk about high-end simulation. What is it? What can you do with it? What is the value, particularly for this given industry? And then I will give you some examples, particularly of some customers from Benelux region where we have done some projects. So, the introduction. Oh, gee. What a surprise. Anyway, next one. So, our company was established in 2011, and that was in the time when I was still working for a SolidWorks reseller in the past. From that business, we started up this company together with another company in UK called SSA. Both companies formed together, were called Simulion, and yeah, we were working together already for a very long time. As per 1st of December, we were being acquired by Adnode, or by TECHNIA actually, to form the TECHNIA Simulation Center of Excellence and to help TECHNIA with the explorations of simulation within their installed customer base. And obviously the PLM knowledge would also be of beneficial help towards our customers. So what are we about? Obviously we are a highly focused group, so we don't do anything else in simulation, so that is what we focus on. So personally I haven't done anything with PLM. I know a little bit about it, I know a little bit about CAD, but I'm not a specialist like these guys. In total, we're with approximately 30 simulation specialists, so developing kind of simulation models and material models, all those kind of things. That makes us actually one of the biggest Simulia providers within Western Europe, and therefore a highly recommended partner from Dassault. What you need to know from the Simulia solutions that we provide is that we don't really focus on one given industry. So I'm now doing a presentation here in civil engineering and construction, but I'm also doing a presentation in industrial equipment. And the reason for that is that with the simulation solutions, we don't really focus on an industry, but we just focus on solving engineering challenges. And they can be in any industry, basically, whether that's life science or civil engineering, industrial equipment, automotive, aerospace, doesn't really matter. Unnecessary to say, but we are fully utilized. We have all stickers and buttons and certifications, obviously, to do everything that is needed to position these tools. So what is then our added value? If you look at the value that we provide, then simulation is all about the knowledge. So the people that we have in our skill set, they come from different areas. We have people who are, let's say, experienced in biomechanical engineering, windmill structures, foundations, earthquake analysis, vibrations, those kind of things. Those are all things that we do. In the world of simulation, there is things which we call linear analysis and non-linear analysis. I'll tell you a little bit about that, what that is. But we mainly focus on high-end simulation, which we see as non-linear analysis, and I'll express that later on what that is. Obviously, because we use the Dassault simulation portfolio, the complete Simulia brand, you can expect to have the latest and greatest technology applied to solve your challenges, and we are very open and collaborative in how we do the things we do. So what is it then that we deliver as the TECHNIA Simulation Center of Excellence? It's a combination of four things. So on one hand, yeah, obviously we provide software. but I don't think we are the generic software provider only, because we are also a customer of Dassault. We purchase the software, we use the software, and if you look at our margin revenue stream as a company, then approximately 50% is coming from services. So mainly a lot of customers who say, oh, that's all very nice, that technology, but we're not going to invest in it. It's too difficult, we don't have the knowledge. So in that particular case, we can do the analysis for them and solve their problem and provide them with a report or a guidance or whatever that needs to be approved to the product or to the process. We also do consulting, support, and training, obviously. So if you need some software, obviously you also need to know how to work with it. So we provide you some training and some support along the way. So what is then the total product portfolio? I won't go into too much of detail what all these tools are and what they do, but it's a little bit much. Our flagship is obviously Abacus. That's the high-end nonlinear FE solver that we use to solve all these difficult challenges, whether that's earthquake analysis or crack propagation in concrete or things that have to do with topology optimization. We have different tools for that. And the nice thing is that all these tools, they can be combined with flexible licensing modules from Dassault, basically. So what do we end up with then? In the world of PLM, and that's obviously the public here today, you know probably more about PLM than I do. But therefore, I thought this slide was quite important. So from software perspective, we have what we call unconnected FE. So those are basically the standalone tools that are not connected to any PLM system or data management system whatsoever. You just do your simulation job, provide the answer, and that's it. The other one is FE connected to PLM. So we have solutions which we call Power BI. We also have that for Abacus, for Xflow, for almost all the tools you just saw in the overview. And that means that all the data that the specialists generate that can be managed in the platform, and you can therefore do simulation lifecycle management. So basically manage your simulation data. You can communicate about the data, and you can also utilize those nice platform technology things like high-performance cluster computing, high-performance visualization, sharing on the cloud, sharing on multiple clusters. That's all available in that new type of software. And then obviously we have the seamlessly integrated software, and those are the exact same technologies, either from Abacus or from the other tools, but then 100% integrated within the platform. So you don't leave the platform, you just open an app in the platform and you just do your thing there. And obviously everything is supported with our knowledge and how we help our customers. So the announcement was about a high-end simulation, but before I talk about high-end simulation, I guess it's important to also understand what the difference is. So therefore I try to explain also what mid-level or let's say entry-level simulation is. And in our view, entry-level simulation is really a CAD-integrated finite element analysis tool that helps you to assess your assumptions during engineering. It's rather straightforward, but these kind of tools, they're really meant for the designers. It's not too complex, but it works very easy, integrated in the CAD environment. And yeah, that's what we see as entry-level simulation. But this is not really what we do. And without going into full detail and all formulas, if you talk about linear static analysis, for the people who don't know, this is a stress strain curve. So if you have a piece of metal or whatever and you try to put it in a tension machine, you see that once you start pulling it, it measures the stress versus deflection in this case. And what you see is that it will first show a linear behavior. So that means that if I make the force twice as big, then also the displacement will be twice as much. That's the linear assumption. But that also means that if you pass this point and you still continue with a linear type of calculation, that your stress will be way too high. So that's one of the wrong assumptions that you do when doing a linear analysis. So that can obviously be solved with something else, and that's what we call high-end simulation. This is obviously the full scope, so therefore there's no red areas here. So we can do the full scope. We can do until the deflection point. We can even go beyond. So when there is failure in the model or in the steel or in the concrete or in whatever type of material, We can also show you how it's going to fail. And I have some later examples how that can be done. So what is then high-end simulation? It is really translating real-world behavior with very complex physics in order to capture the full behavior and have good predictive models. That's what it's all about. And obviously these can be realistic, accurate and powerful and versatile. I mean, such a thing like the living heart, I think it's been discussed already many times or mentioned many times. But if you think about all the physics that are in a simulation model of a heart and what is driving that, it is really all the muscles being modeled. There is a piezoelectric current driving those muscles. Those muscles are being contracted. The contractions have interaction with human tissue. The human tissue is actually modeled. So this is not just a rubber kind of material. It's really human tissue that is modeled here. And that is how you can make your predictions accurate. Obviously, that's a whole journey of validating your model, making sure you have the right material assumptions. But once you're there, it's very valuable to be able to optimize your products and your processes. Okay, so back to AEC. So what is it that we can capture in a total with the help of high-end simulation? Now, obviously, these are pretty common things, but if you think about structural configuration, there is many solutions to basically, bridge the gap, if you would like to mention that. So you can have construction A, B, C. So you need to assess whether all these trusses that come together, if they will hold, if they have a certain amount of lifetime, what is the fatigue amount, if it's built from steel. How will it be connected? Will it be bolted? Will it be welded? Those kind of things, they can all be assessed. Same as with material behavior. Obviously, within your industry, we see a trend of using more exotic type of materials, whether that's honeycomb structures, composites, plywood. It could basically be everything. Those are things you can take into account. And also environmental conditions, obviously, that can all be used as an input. So, if we talk about structural analysis, that is what we call strength analysis, or things where you want to assess basically the strength or the displacements, or will it fail, yes or no, and if it fails, how does it fail? Those can be done with structural analysis. So, if we talk about abacus, then that is mainly about doing nonlinear analysis. And nonlinear analysis, we already discussed that graph. But we have a distinction in there. So you can have nonlinear forces, nonlinear contact, nonlinear material, and we discuss them as we go. But I guess you can imagine that something like an explosion is not really something like a static force. It's really a dynamic force, and a force that grows and that becomes bigger. There's a pressure wave, and that all needs to be incorporated. Same here. You have a dynamic load of a train going over a rail. Maybe you want to assess the amount of frequencies or vibration in a building due to a train passing by. Those are all kind of dynamic analysis, which makes it rather nonlinear. And a good example of earthquake analysis, obviously. Then the next nonlinear tail is a material. So if you think about the first linear curve, that would be steel if you don't do any plastic deformation. But there's obviously more complex materials, things like rubber, things like concrete, things like soil. In here you even see a model of the World Trade Tower where they did an investigation on the damage accumulation. Could it be really caused by the fire in the structure that is causing the steel to become weaker and to have softening basically by the thermal load? The answer is yes, obviously. So those are the materials. Then we have things like contact. So once you have multiple parts in contact, then the world becomes very nonlinear because there is no standard thing in contact. So once things go slipping, or there's friction, or there's movement, or bricks falling off a wall or whatsoever, that's all very dynamic. And that's what we can model with abacus very, very accurately. So Most of the things we do have to do with something that is being driven by risk. Either they want to make sure that their investment is safe, so they don't want to put all the money and then have a building that basically collapses or does something like that. So it's all about risk assessment. So will it fail? Will it hold? If I'm standing here as a person and there will be some movement or some wind loading, can I still work comfortably there, or will the whole building start shaking? Which is not really uncommon, by the way. New materials, how will they behave? We already discussed honeycomb structures or things like composites, fiber reinforced concrete. Also kind of a nice to use material that a lot of people are working on these days. Then performance-based design, those are really the type of structures that are really heavily loaded. Think about an extreme dam in this case, or a nuclear power reactor. Obviously, there's very different specifications in these kind of structures to do the design. If you look at a nuclear reactor, there's even specifications where you have to make sure that the structure keeps on standing there if something flies in or not. So those things can be really assessed. Also, the lifetime of the concrete is very important in combination with all the steel reinforcements and the rebars and the thermal aspects of that. So that can really be modeled and be simulated. That was mainly about structural analysis. Another area of our business is to do computational fluid dynamics. So basically, flow simulations. And this is a nice example here of a football stadium. But the things we can really assess is, so what will this thing do? If there is a certain wind from a certain direction, will these people still be comfortable, yes or no? What are the actual wind loads on the facade, for instance? Will they fly away if there is a storm, or will they stick on its place? Those are all things you can assess. And we can help you with that, obviously. Next one. So wind loads. If you see the wind loads on a bridge, I guess everybody has seen the Takuma bridge with the moving bridge. That wasn't a consequence of modal frequency only. What they probably didn't tell you in the full story is that frequency was basically caused by the wind loading. So the wind loading was around all these stays basically, and if you do that, all those vortexes of the wind, they go behind all the tension bars, and those vortexes, they start letting the whole structure move. And once it starts moving, and apparently that frequency is in the close area of its natural frequency, then you have a problem, because then the whole structure will start moving and will only get worse and worse and worse. So that's something you can assess with simulation. This is another wind speed analysis. Obviously, this is more for cities. So the effect that you get if you have multiple buildings together, you will create these kind of Venturi situations. So we even had a situation in the Netherlands where they built a subway, and they forgot to do these kind of tests. So then you had a train passing by the station, but all the turning doors on the outside of the train station, they would start rotating once the train was passing by. So I don't think those are really nice situations to be happening, and that is something you can really assess beforehand. Yeah, so another thing that we do is, this is what we call fluid structure interaction. So what you see is that basically in normal language, this structure is being driven by a flow. I think that's the most appropriate way to say it. So if the wind is starting, then the propeller will start rotating, and you want to know how fast it will be rotating, what the angle of the blades will be, how it will impact the total structure. If you have a foundation, you need to know what the forces are due to the wind. You can actually assess this, whether there is also multiple codes that you need to apply to, but if you really want to know it, you can really simulate it as well. Same with water management. Also in the Netherlands, we are pretty famous on living below the sea level. So we have all kind of issues with this. In Rotterdam, they have a very famous square where if it starts to rain, the whole square is turning into a pond, basically. And it's being done deliberately. So they have all these systems to basically capture the water and make sure it's nice. It doesn't bring you any harm or any stuff. And those things can really be simulated beforehand as well. Other things like bridge pillars. Obviously, you see water coming here with waves hitting the foundation. As an engineer, it can be very complex to assess which loads are basically coming from the tidal water, and that is something you can bring into account by doing these kind of analysis. Same with the dam break. In here you see correlation to experimental data. So green is what is tested, and black is what is measured. So you see that the data is very, very correlated, and therefore predictions are very, very accurate. Another area that we do our work in is internal comfort, so HVAC. So this is all about thermal, personal comfort in buildings, amount of moisture. We also do a lot of things in clean rooms, where people need to be able to predict whether there will be some dust or some moisture, or how to prevent that, basically. So that's also something we do. On the bottom left, you see an example of a smoke simulation of a metro subway. So you see the smoke being induced by fire, and obviously the smoke needs to go up, and you want to develop a system basically that can capture that and get rid of that. And on the right-hand side, you see a dispersion of industrial gases. We had some accidents in the Netherlands as well, where they had some very toxic gases coming out of oil plant, and they needed to do a root cause analysis where the potential spread of the toxic gas would come, and in which area of the city, and what could be potentially infected. So those things can be simulated as well. Next one. That's all about thermal. So thermal application is also something you do with CFD. So this is a very nice example of anyone opening their fridge. This is actually what happens if you open the fridge door and you leave it open too long. So you actually see the cold air falling on the ground. If you wouldn't wear any shoes, or you will be at bare feet, you would actually feel the cold around your feet going down. And this is what is virtually happening. So that's also with these simulation tools, you can virtually see things that normally are very difficult to predict, and you can change your design and make sure that the person in the cabin or wherever is feeling comfortable. So then, as a short summary, what value does high-end simulation then bring? Well, obviously, in my perspective, it brings a lot of innovation, because you can bring value, and you can see things that you normally couldn't really see. A lot of the things that we do is also about cost reductions. So normally it's really contradictory, because the product performance should be better, but it should be lighter, it should be cheaper, but it still should be stronger, actually. So that's a very difficult task to do, and I think it's almost impossible doing that without simulation. And obviously you see the products that can be very simple, but have a lot of complexity in it, and those really bring distinctiveness. So those are most likely the products that are really being thought about with help of simulation. So then some examples. This is one of our customers in Benelux. It's called TNO. It's a research facility. And what you see on the left is one of our bridges. One of the issue in the Netherlands is that we have a lot of bridges, and they are all pre-World War II. So they were there already for a long time. These are steel bridges, and they were designed in an area or in an era where there wasn't the amount of cars that we have today. So that was one of the major issues. We had a real big incident in the Netherlands where in 2016 they had to shut down the highway, and this was the A27, which goes from basically south to north of the Netherlands. And the reason for that was that they find cracks in the bridge. So in this area, if you see this beam structure, they found cracks that were so big that they need to stop all traffic immediately. They didn't realize how lucky they were and they did realize that later on. So in 2019, actually in January, a report came out how close they were. But once you see it, you still have to make it better. So in this case, TNO did all sorts of calculations how they could quickly get a fix to make sure the bridge is not collapsing and that the traffic could easily go over that again. So what they basically did is they created all these kind of structures on the bottom side, which they bolted, they plated together and make sure that they do additional checks. This bridge doesn't last very long. Plans are now to replace the complete bridge before 2021. So this one is off. But we help the customer assessing this. We also help them with the use of Abacus, where they could really assess what to do and how to improve the design to make sure that the bridge did not collapse. And luckily it didn't. Or else we would be ending up with those Italian issues. This is a different customer. They're called Deltares. They are all about water management and soils. So these guys know a lot about dams and dikes and those kind of things. But this given product they did was a very specific one, because they needed to have a prediction of the Mars lander on the surface of Mars. Because if you design a Mars lander, you need to make sure that the wheels that go and start rotating over the surface of Mars, that once that thing lands there, that it shouldn't get stuck, basically. And you don't want that, because once it's stuck, you can't really get it out anymore. So they did all these kind of simulations. They did all kind of assessments on the type of soil and the interaction of the soil. And they needed to have the wheels potentially rotating on that soil. So that's what they did. They also do a lot of things about dams and slope stability, and we help them with their knowledge. This is something that we did for another company in the Netherlands. I also know that they're in Sweden, Sweco. But in this particular case, they were having different tools than Abacus. They always used Diana, which is a development from the University of Delft. And with that tool, they were facing some difficulties, and they wanted to move into doing a proper automated way of running these analyses. And in the north of the Netherlands, that's called Groningen, the Groningen province, we have a lot of issues with earthquakes these moments, because they pump gas, natural gas, they pump that out of the ground. And due to that fact, there is a lot of earthquakes. How funny. So now they have to solve that. They have to restructure all the houses. They have to stiffen those. They have to repair them, which is a big issue. So these guys are actually modeling the houses with all the concrete and all the masonry in between, and they are doing root cause analysis to predict whether it's a crack that came from an earthquake or whether it's a crack that came from somewhere else, because obviously this is a money question, because who's going to pay for it? Is it the government? Is it the people who get the gas out of the ground? It's a major issue. But these guys do the actual assessments on the houses, and we helped them to do so. This is a different customer, Boskalis. They are quite unique because these are the guys in the Netherlands who produce all these open porous asphalt. So if you have ever been driving over the roads in the Netherlands, you don't have any spray of rain when it's raining. It's very comfortable. But the issue is that they were one of the first laying that top layer in the Netherlands. And then they found out that the top layer is not meeting the life estimation criteria that they promised, basically. So they promised something like 25 years, and it barely hits 10. I believe I've been told that a piece of tarmac, so let's say 1 kilometer of tarmac, costs 1 million plus. So if they need to redo a piece of road, it's pretty costly. So they only have one chance to make this better, and therefore they want to have an optimal mixture of the porous asphalt to make sure that it would meet the next lifetime estimation if they need to redo it anyway. Because they only have one chance to make the new tarmac, and then it should meet the criteria. So what we basically did for them, and you see that completely on the left, we had a drill of a piece of road. We scanned it in 3D with a CT scan. We made 3D geometry of that. We then built a simulation model on top of that. We put some forces, some traction, rolling tires, and then we developed a model that Boskalis can use themselves where you see here, in those boxes below, they can play with the amount of aggregate, the mortar, the voids, and do all their mixture predictions, because basically tarmac is a combination of mixture of many ingredients, and certain ingredient can meet criteria, yes or no. So that's what we help them with. Last but not least, it's TU Delft. They do a lot about also earthquake analysis. So this is a pushover wall test. So they build a wall and they want to know whether the finite element analysis tool can fully predict that accurately. So they've done all these practical setup tests. They also do steel fiber pull-out tests. So if you have these new type of concrete structures where you have metal fibers embedded in the concrete, they need to know what the resistance is of pulling out those fibers. That's also something they do, and we help them with. And this is really the last customer case. This is ArcelorMittal, large world's biggest steel producer. They do a lot of steel for the civil engineering industry. Obviously, they also do a lot about facade engineering. But what you actually see in the middle is the actual weldment process. So once you have plates that are welded, there's a heat beam going over the surface. The metal is changing from its characteristics because there is a hardening effect. And you need to take that into account in the total structure. So we're not only doing the actual products, but in this case, it's also a process which is the welding process that we simulate.